Welcome to this Geogebra tutorial, second lesson of teaching mathematics differently with Was Moses. In this lesson, we shall be looking at how to factorize polynomial functions using the CAS submenu in Geogebra app. As lesson objectives, this lesson will help teachers to prepare better lessons on polynomials. It will help them identify factorizable polynomial functions before giving to students. It will also help students identify the graphs of a function with at least one double root. As a recall, a factor is an exact divisor. For example, if we say 9 divided by 2, the answer is 4 with a remainder of 1. 9 divided by 3 is 3 with no remainder. In these cases, we say that 3 is a factor of 9, but 2 is not a factor of 9. 3 is an exact divisor of 9, while 2 is not an exact divisor. To better understand this on Geogebra, let's practice the factorization method using the following example. The first example is a quadratic polynomial. The second is a cubic polynomial. Third, another cubic polynomial. And the fourth example will be a quartic polynomial. Let's begin the Geogebra illustration. We get the Geogebra app. For those who don't have it, they should always download and install it in their laptops. When you get to the Geogebra app, click at this top right corner. Choose the CAS submenu. As you see, you follow the steps. When it is chosen, you close all the other selected menus that were open. Good. On our screen, we now have the CAS submenu. You see one indicating where you have that one, it is an input. It is where you input your function. We go directly, we input the functions, and we see what we have. The first polynomial function. Good. This is the function. Now, how do we factorize this function? We go above where you have the display submenus options and take on this option. This option 15.3.5 shows factors. So we click on it and we get the factors of the polynomial x squared plus x minus 6 to be x minus 2 into x plus 3. We move to the second. We input the polynomial also. That polynomial gives us a cubic polynomial. Again, we do the same. We click on the factorization option. And the result is as follows. G of x, the factors of that cubic polynomials are x plus 3 into x squared minus 6. And k should be taken here. This x squared minus 6 can no longer be factorized. That is why you see it as a quadratic factor. We move to the third example. Our third example is still a cubic polynomial. We input it and we see how the CAS menu will do the factorization. Good. Once you input the function, you get directly to the factorization option and click there. Again, we have our linear factors. Once the linear factors are, or all the factors of the polynomial are linear, it gives us that that particular polynomial could be completely factorized. We move to the next example, example 4. We get the quartic polynomial. When we input it, we follow the same steps as above. Good. We now see the factors. All these four polynomials have been factorized. But when you look at the fourth example, you discovered that there is a special case of a double factor. This double factor, what does it imply? It implies that at the root x equal -2 for this quartic polynomial, the graph of the function p of x will have a turning point at x equal -2. This concept can also be shown still using the CAS submenu. How do we do this? We simply get the derivative of this polynomial, p of x, and show that at the point x equal -2, the derivative is 0, which is a sufficient condition for a turning point. How do we get the derivative? After the polynomial has been input, we move to the display options and we take f prime. This f prime means the first derivative. So we click there and the result is the derivative of that quartic polynomial. Okay, we said that at 4, that when x plus 2 is a double factor, it's a repeated linear factor, that repeated linear factor shows that at the point where x satisfies that repeated linear factors, the function is turning, meaning that the graph of every function with a double root has a turning point at that double root. To verify this, as we have already said, we just need to move to that derivative. We substitute the root -2 in p primes of x, and we show that it is 0. It is very simple to do in the CAS submenu. Please watch carefully. I simply take input the derivative as I have done. And now what do? I substitute. In the CAS options, we can also substitute. We move to this input box, 7, this. It shows that this is an input box. You can input every given value in a substitution. I click there, you see all expression is x, new expression. I want that this x should be replaced by -2. So I will click on new expression and take -2 equals to. Wow. You see exactly. Yeah, our assumption has been clarified. Now, the next thing we need to do is I will display all these 4 factors here so that I use the first 4 factors to show in a graphic that actually where you have these linear factors like this, the values of x at all the linear factors satisfy the roots of every given polynomial function defined in each of the 4 above examples. So please, just keep on following and get the concepts. And what I'm trying to show here is that when you have a function with when you have a function that has already been factorized, please, that function that has been factorized can be expanded to obtain the required polynomial. In the CAS submenu, you can still do the expansion without necessarily writing down anything. Okay. Okay, please, let me just show an illustration of one. Look at this. Let's get to 10 p of x. If p of x was given in terms of its factors, to expand this, we simply click there, and you go to this. This option gives the expanded form. So if I click here, that factorizable form becomes expanded. And that is actually what we obtain. Okay, please. Now, the last thing I want us to understand is when you do this type of factorization in CAS and you are doubting whether those factors are actually the factors of the given polynomials, there is also a way of verifying. And how do we verify? To be able to verify this, we go back to this menu, we click we bring in the algebra room. We still click there. and we bring in the graphic room. Okay, please, with this graphic interface, we just simply need to put down each of these functions. The first one, we copy and we paste, enter. I don't want to have the graphs yet. At the end, we'll display the graphs, and we see that each of those graphs has a root where those factors at each linear factor, please. Instead of typing all these functions, it is easier to just copy and paste. That is simply what I'm doing. For the 4 given examples. For the 4 given examples. Okay. Okay, please, what I am trying to illustrate is making us to see the functions of all these 4 examples. If I click on this, I bring the function, the polynomial function. And from the factors, we do notice that x plus 2 into x minus 2 into x plus 3 shows that there is a root at -3 and there is a root at 2, which can be clearly seen from this graph. Okay, now, in the second graph, g of x, which is a cubic polynomial, this one shows that if I seek this for us to see the factors, this one shows that 7. There is a root 2 at -3. Okay. If I click there, -3, you see the root. There's a root at -3. Moving to the next, h of x, that polynomial shows in the factorization that there are 3 linear roots, a root at 2, a root at -1, and a root at -1.5. Let us verify from the function. A root at -1, a root at 2, and a root at -1.5. We move to the last polynomial. And that last polynomial was a special polynomial. We identified that there is a root at 1, there is a root at -1, and there is a double root at -2. And we said that that double root implies the polynomial has a turning point at -2. Geometrically, let us look at the graph. Good. Now, if I seek or bold this graph, you see exactly what we are talking about. Look at -2. -2 is the case of that double root. And in the case of that double root, we have seen that the double root at -2 is actually a turning point, thereby just confirming what we have already proven in the CAD submenu. Please, thank you for following. And if you did watch the video, just go to the right and click on the subscribe option to subscribe to this YouTube channel, because more interactive lessons on Geogebra will be uploaded. And please, just also click on like as you follow the videos. Thanks once again for following, and we'll always keep in touch.